Hello, friends. Welcome to the hydraulics and hydraulic machinery class. So, we are discussing about the critical flow, that too focusing on specific energy. In the previous lecture, we discussed the introduction part of specific energy and then the specific energy curve. In today's lecture, let us discuss on the conditions for minimum specific energy. In other words, the conditions for critical flow in general, and of course, a rectangular channel in particular. That's the first thing. Then we will go for what is the relation between discharge and critical depth in case of a given channel section and specific energy. So these two things we will discuss today. And these are all the main, very important things in this particular critical flow topic. So let us straight away take up that. Today's discussion will focus on number one, conditions for critical flow. Number two, conditions for minimum specific energy. Condition for maximum discharge. First, let us discuss on for a given channel section and given discharge, derive the conditions for critical flow. Now I start any equation in specific energy if anything is asked. Let us start always with the fundamentals. That is E is equal to Y plus V squared by 2G. This is also can be written as Y plus Q squared by 2G A squared. This is our base equation. So now conditions you see, number one is for a given channel section and second thing is given Q. That means here channel section is same and Q is a constant. So what is the condition for basically the minimum specific energy? For minimum specific energy, mathematically we can write dE by dy is equal to 0. So let me solve that. So what is dE by dy? It is equal to d by dy of y plus q square by 2ga square. It is equal to dy by dy 1, right, plus q square by 2g into a square. If it goes to denominator, a to the power of minus 2. Then if I do it, it is minus 2 into a to the power of minus 3 into dA by dy. So if I take it, basically 1 plus and minus, it will become minus 2q squared by 2g into a to the power of minus 3 means in the denominator it becomes a cube into dA by dy. So this is equal to what? 0. So therefore, in this, if I look at what is this dA by dy, suppose if I take a channel like this is a channel section. So I take basically a small strip. So this strip thickness is dy and here this top width is t. So this area dA is equal to t into dy or dA by dy is equal to top width t. So if I do it, 1 minus 2 will cancel, q square by ga cube into t is equal to 0 or q square t by ga cube is equal to 1 or q square by g is equal to a cubed by t. This is the general condition. U square by g is equal to a cubed by t. By writing like that, I wish to tell you 2 points. Number one is this is condition for minimum specific energy. This is also condition for critical flow. How? You can ask me how, sir. So let me take it actually. For q square by g is equal to a cubed by t. So I can write q square is equal to a square v square by g is equal to a cubed by t. So this a square if I cancel, then v square by g is equal to a by t, right? If I write it, so then or what is a by t? We know actually it is nothing but hydraulic depth d. That means v square by g is equal to d, or I can simplify v square by gd is equal to 1. So v square by gd is equal to 1 or v by root gd is equal to 1. Already I told you number of times this corresponds to the Froude number is equal to 1. So Froude number is equal to 1 means what actually for you? Froude number 1 means automatically it is actually critical flow condition. So that's why I told. So first thing you should understand here, the conclusion point here is like this. Conclusion point is the number one, at critical flow for a given channel section, for a given channel section and given discharge and given discharge, The specific energy is minimum. This is first point. The second point we should understand is for critical flow, the condition is E is equal to minimum, which we will write it as E minimum, and then Q squared by G is equal to A cubed by T. And this equation is applicable for rectangular, triangular, trapezoidal, or circular channels. Any type of channels, this is applicable. So this is one part first. Then I will go into the most second important point is generally at undergraduate level, normally the critical flow we deal with rectangular channels. So in case here only, but otherwise at next level we go for triangular, we go for basically the trapezoidal or circular. All we will take it up at a later stage actually, right? But here at this level we will not take actually the other things. So for us most important thing is only rectangular channels. Then derive the condition for critical depth, which is very very important. Critical depth in rectangular channels, because at this level we concentrate more on rectangular channels. So I will take up that independently, right? You can do from the previous one also, you can do it independently also, you can do it. So now what I will do, I consider a rectangular channel of base width B. This is Y. I assume it as YC. This is B, right? So now base, if I take it, what is the equation? E is equal to y plus v squared by 2g. That also can be written as y plus q square by 2g a square. This also can be written as y plus small q square by 2g y square. Why, how you can write like that? Then small q is nothing but q by b. This is discharge per unit width. Therefore, naturally for us, if I do it, what for minimum specific energy, for minimum specific energy, dE by dy should be equal to 0. If I put like that, so d by dE by dy is equal to 0, or d by dy of y plus q square by 2g y square is equal to 0. So if I analyze it, 1 minus 2q square by 2g y cube into dA by dy. dA by dy is nothing but actually q square by 2g y square y cube into what is dA by dy? dA by dy is nothing but actually it is only basically again, yeah, we need not it's nothing like y, sorry, is equal to is equal to 0. So 2 I will cancel. 1 minus q square by gy cube is equal to 0, or q square by g is equal to y cube, or q square by g is equal to yc cube, because When E becomes E minimum, Y becomes YC. If you want, here you can note it. When E becomes E minimum, Y becomes YC. So therefore, YC cube is equal to Q square by G, or YC is equal to Q square by G whole to the power of 1 by 3. Excellent equation actually. Again, remember critical depth is equal to Q square by G whole to the power of 1 by 3, and this equation is applicable to rectangular channels. I can do from this actually you want, then we know for the for critical flow VC by root GYC Froude number is equal to 1. Therefore, VC is equal to root GYC, that is critical velocity is equal to root of GYC. This is the second thing that you should remember. So I have completed two important things. What are the two important things? Number one is condition for minimum specific energy is Q square by G is equal to A cubed by T, and then condition for critical minimum specific energy in rectangular channels is it is YC is equal to Q square by G whole to the power of 1 by 3, and VC is equal to root GYC. Then I will go into the next condition actually, minimum specific energy. Minimum specific energy in terms of critical depth. You express it in terms of critical depth. How we will do it? Again, I will take it actually. E is equal to, always starting point is v square by 2g is equal to y plus q square by 2g a square is equal to y plus small q square by 2g y square. This is the basic thing. As when the specific, as specific energy is minimum, as specific energy is minimum, what is the condition for minimum specific energy? The depth of flow is critical depth. Then only specific energy will be minimum. So that is the condition. So therefore, E minimum is equal to, when this becomes, then here it becomes YC plus Q square by 2G into YC square. So now I can write this Q square by G is equal to, this is equal to YC cube. So therefore, if I make it YC plus YC cubed by 2YC square, it is YC plus YC by 2. It is equal to 3 by 2 YC. So therefore, E minimum is equal to 3 by 2 YC. In this 3 by 2 YC is the critical depth, and half YC relates to the velocity head. Kindly remember that. That's what YC plus YC by 2, or else YC is equal to 2 by 3 into E minimum. This is again very useful, these equations, while solving the problems. Here I can see that actually this is another thing. So the last one which I will derive is what is the condition? What is the condition for maximum discharge? Condition for maximum discharge for a given channel section and given specific energy. So this is the question. So again, condition for maximum discharge. Previous one, what we had done, condition for minimum specific energy. So now if I take it this E is equal to y plus v square by 2g, or it is equal to y plus q square by 2g a square. It is equal to y plus small q square by 2g y square. This is the basic thing. Now what I mentioned, so if I see this, then E minus y becomes, if I bring this, it is equal to q square by 2g y square, or q square is equal to 2g y square into E minus y. So or basically q is equal to, then actually if I take it, root of 2g into ey square minus y cube. Am I right? If it goes inside, actually it is ey square minus y cube. Perfect. So for maximum of q, ey square minus y cube should be maximum because g is constant. For maximum of ey square minus y cube, d by dy of ey square minus y cube is equal to 0. Therefore, it will represent 2ey minus 3y square is equal to 0, or then 2e is equal to minus 3y is equal to 0, or e is equal to 3 by 2y. So what is this? This is nothing but for maximum discharge. Maximum discharge E is equal to 3 by 2y. When this is possible, actually, this is possible only, this is possible only, this is possible only in case of critical flow. That is, discharge is maximum if flow is critical. This same I can explain by a diagram also. If I take an x-axis, y-axis, on x-axis, if I take it actually small q, and on y-axis, if you take depth of flow, then actually the curve is, and I have taken this curve will be like this. And if I write here, which is constant, E is equal to constant. That is the condition, right? If I draw like this, it will be. So if I see here, this is the maximum discharge. So for maximum discharge, here flow is critical. That is y is equal to yc. So in this region, if you take it in this region, actually, this region y is greater than yc. That is subcritical flow region. So this region actually, if I take this region here, y is less than yc. So this is supercritical flow. super critical flow region. So this diagram is called as discharge diagram. So we have given you two diagrams actually in this. One is specific energy diagram, wherein on x-axis we have taken specific energy and y-axis depth of flow. That is for a given discharge. Whereas here we are taking discharge intensity on x-axis and depth of flow on y-axis. This is for a given base thing, what you call it as specific energy. I can write this depth of flow is nothing but yc actually, and yc is equal to 2 by 3 times e. So this is the one of the important things. Now to summarize the whole, I will write point by point, kindly concentrate. So what are the critical flow characteristics? This is the conclusion of Kia. Critical flow characteristics. So if I start analyzing it, number one, if I take it for a given channel section, see how I am mentioning for a given channel section, this is one condition. And second section is for a given discharge, specific energy is minimum. This is for the first condition for critical flow. If I go for second condition, if I take the second condition again for a given channel section, right? For a given specific energy discharge is maximum. That is second condition. Third condition is, if I take it, the equation for specific energy is y plus v square by 2g, which is equal to y plus q square by 2g into y square. Sorry. So this is the third. What is the fourth actually? Critical flow condition. General, any check section. Critical flow condition is q square by g is equal to a cubed by t. Here itself I can write for rectangular channels. The critical depth yc is equal to q square by g whole to the power of 1 by 3, or q is equal to q by b. This is fourth. Then fifth, actually, E minimum is equal to yc plus yc by 2 is equal to 3 by 2 yc, or yc is equal to 2 by 3 E minimum. This is again another condition. The last condition is for critical flow, Proud number is equal to 1. Fr is nothing but the Froude number. is equal to 1, right? In that case, Y is equal to YC. Then for subcritical flow, FR is less than 1. In such a case, Y is greater than YC. Then supercritical flow, Proud number greater than 1, Y less than YC. So these are the 6 points we should understand for critical flow. So I will stop the lecture here. So what are the takeaways in today's lecture? Number one, first thing is for a given section and discharge, both. That means channel section and given discharge, and that means discharge is constant. Then for critical flow, specific energy is minimum. If the specific energy is minimum, that flow is called critical flow. And what is the condition for that critical flow? Q square by G is equal to A cubed by T. And for rectangular channels, what is the condition for critical depth? YC is equal to Q square by G whole to the power of 1 by 3. What is Q there? It is capital Q by the width of the channel. That's all first point. What is the second point? For critical flow, the discharge is maximum. That is second point. Then third point and is Froude number is equal to 1. This is for critical flow. So the and what is the equation? The minimum specific energy is equal to 3 by 2 into critical depth. Then next, what is critical velocity? Vc is equal to root gyc. And what happens to the Froude number? Froude number is equal to 1 in case of critical flow. Suppose in case of subcritical flow, Froude number is less than 1. In case of supercritical flow, Froude number is greater than 1. So these are the things that we should remember.
Like, share, and subscribe. Hit the bell icon for more updates.